Over 80% of Canada's emissions come from the energy and transportation sectors. If Canada wants to reach its net zero goals by 2050, we must come up with cleaner energy options now. Introducing the rotating detonation engine. The rotating detonation engine uses supersonic combustion waves called detonations. Detonations travel faster than the speed of sound, and when they're used in an engine, they can create cleaner engines that are also compatible with clean fuels like hydrogen. Detonations are relatively well understood in gaseous fuels. However, detonations are poorly understood in liquid fuels. Liquid fuels are incredibly important for the widespread adoption of these engines due to their superior volumetric energy density and for their increased safety. For example, if you had hydrogen in its gaseous form, you would need a volume 10 times the size compared to if you used it in its liquid form. This is where our research comes in. Our research uses a detonation channel. A detonation wave passes from left to right through the channel over a droplet cloud. A fuel injector injects these small, monodispersed droplets into the channel. As the detonation wave passes over these droplets, high-speed imaging called Schlieren is used, as well as soot foils. Soot foils are where you place soot on a thin sheet of metal and place it inside the channel. Once inside the channel, and the detonation wave passes over it, it leaves behind these cell sizes. These cells are quantified using the soot foil. The soot foil shows that these cell sizes, these diamond shapes, are similar to a fingerprint and help us to understand exactly how the detonation propagated. On the screen is a simulation of a soot foil. On the left-hand side, we see the detonation start in solely a gaseous form. At the 10-inch mark, we see transition to including small monodispersed droplets. At this point, we see these cells, or diamond shapes, transition and become much larger. At this point, we see the stability of the detonation has significantly changed, and that has a large impact of the stability of the detonation. This has incredible impacts on whether or not we can use these detonations in an engine, so it's important we understand how the cell size changes with a liquid fuel. However, these simulations are not validated in real life. We need to be able to understand how this simulation compares to real-life data to be able to understand if these detonations can be used in these engines. That's why it's important that we have experimental data to compare to these simulations. Our research is critical for closing the gap between clean fuels and clean energy engines and ultimately a cleaner future for tomorrow. Thank you.